people. Today we have a challenging lecture, so we have to pay a lot of attention. So as we have discussed previously, so when we have two kinds of collisions. We have elastic and inelastic collisions, right? So what we should know is that for the elastic collision, the linear momentum is conserved. So that implies that the sum of linear momentum initial is equal to the sum of all the linear momentums final. And also the kinetic energy is conserved, which also says that the kinetic energy initial is equal to the sum of the kinetic energy final, right? So the linear momentum is a vectorial property, is a vector, the linear momentum, and the kinetic energy is a scalar, is just a energy. So on the other hand, for the inelastic collisions, we only have the condition, the conservation of linear momentum. The sum of all the linear momentums before the collision is equal to the sum of all the linear momentum after the collision, right? So I've seen lots of issues with this particular problem that we asked you to solve the other day. This one in particular, a proton collides elastically with another proton that is initially at rest, right? So let's actually solve it. The incoming proton has an initial speed of 3.5 10 to the 5 meters per second and scatters off 37 degrees with respect to the horizontal in the x-axis, and is asking us what is the scattering of the other particle or the other proton, and find the final speeds and the angle. So okay, let's just do it. For that, we are going to make the problem here. We're going to need a few pages. So we have initial, we have a proton, right? And we have a proton which is not moving. So V2 initial is equal to 0, and V1 initial is equal to whatever, that velocity that we mentioned before, which was 3.5 10 to the 5. Okay. So 3.5 10 to the 5 meters per second. So we have to differentiate here in terms of before collision, what's happened, and this will be represented by the sum of P initial, right? And what happened after the collision. After the collision, we have M, this is M1 and this is M2, but as they are all protons, right? This is also a proton, so M1 is equal to M2, and we're going to call it just M. So again, this was our reference frame, right? This was our reference frame. This is X, and the same thing we have here. We have a reference frame X and a reference frame Y, right? So one proton, M1, let's call it M1 because we know, goes with an angle of, let's call it theta 1, 37 degrees, right? But the other one comes with another angle that we don't know, let's call it theta 2, and this is the particle which goes with a velocity V2 final, and this is V1 final, right? So again, the sum of the P final, these two will be equal because we have conservation of linear momentum in any collision, whether it's elastic or inelastic. This term obviously will be just M1 or M, we call it M, V1, because V2 is equal to 0, but this term And now actually we decompose on terms of x and y components, right? As we always do. And PF, let's go focus on x first, will be mv1 final. That will be the cosine of 37, and then this also will be positive, plus mv2 final cosine of this theta 2, which we need to know, right? So now if we put these two equations together, let's open a new board here. We will have that initial conditions before the collision. We have m1 or m actually v1 initial equal, let's remove the 1 from here, so equal to m1 v1 final plus m2 actually with the, I forgot the cosine, v2 final cosine of theta 2, that's the one we need to know, and here was the cosine of theta 1, which we know is 37 degrees, right? All right, so we have equation 1, which can be actually simplified because m1 and m2 are the same, so we have v1 initial, this always we're talking now on the x-axis, is going to be equal to v1 final cosine of 37 degrees plus v2 final cosine of theta 2. Alright, so now we look at what happened in the y-axis. Let's remind ourselves about the problem. So we have x here and then y here. This goes here with an angle theta, and this is the ball, so this is v1 final, and this one here is v2 final, right? So this is equation 1. Equation 2 will be on y. We have that 0 because initial velocity, everything moves on the x-axis. The particle which was incoming here is only moving on the x-axis, right? It's not doesn't have any y component, so 0 before collision, always before collision, is equal to what is happening after collision. So we have v1 final. Now on y we will have sine of 37 degrees plus actually minus, because in the negative axis, this particle 2 is moving down in the y-axis, minus v2 final sine of this angle that we need to determine, theta 2, right? Okay, this is a second equation that we may need later on, but so far as we see, here we have these cosines, and here we have this cosine, and here we have the sine. So when we have this sine and cosine, we have two equations that we cannot add and subtract to get rid of something. The typical line of thought is to say, okay, we know that the cosine square of theta plus, in trigonometry in general, by the sine square of theta is equal to 1. So as keeping this in mind, let's square this equation and see what happens. So if we square the two of them, we have 1 square equal v1 final square cosine square of 37 degrees plus v2 final square cosine square of theta 2 plus 2 v1f cosine of 37 v2f cosine of theta 2. Right, that's for the first equation for the second equation, we have 0 equal v1 final square sine square of 37, right, minus, actually plus, sorry, v2f square sine square of theta 2 minus 2 v1f sine of 37 degrees v2f sine of theta that we don't know. Okay, so now we have reached an equation that actually it makes sense, because now we can add these two, and as you can see, we adding the two of them, we have v1 initial square equal v1 final square, and then we have cosine of 37 and sine of 37. This plus this is equal to 1, so that will go away, plus then we have v2f cosine of square here, and then we have v2f sine square here. So cosine square plus sine square is equal to 1, so there will be v2f square, and then plus the whole thing here plus 2v1f cosine of 37 v2f cosine of theta 2 minus 2v1f sine of 37 v2f sine of theta 2. Okay, and here we have this equation that we're going to keep in mind, because keep in mind this term, and this term. Actually, we can still simplify it. We can still simplify this equation. v1f is the same, v2f is the same, so cosine of 37 cosine of theta 2. Okay, we can keep simplifying this. We're going to have something like this. Let me see if I can remember this. Oh, sorry, we want to open a new one, and we're going to have v1 initial square is equal to v1f square plus v2f square plus, and if I remember well, it was 2v1f v2f, and we have cosine of 37 cosine of theta 2 minus sine of 37 sine of theta 2. Okay, as this is a movie, you can always go back easily. I had to somehow figure things out, but now we have equation 1. And now, as we know, we have an elastic collision, because we have a proton incident on another proton, and there's no interaction, internal excitation of the proton. So the particle scatter, and this goes scatter. So we know that also the sum of the kinetic energy initial is equal to the sum of the kinetic energy final. So easy to say, 1/2 of m1 v1 square, v1 initial, is equal to, remember, v2 initial is 0, because this proton is equal to 1/2 of m v1 final square plus 1/2 of m v2 final square. We can cancel all this 1/2 of m, because they're all everywhere. So we have something which looks like this: v1 square is equal to v1 final square plus v2 final square. So we have yet a second equation, which, as you can see, it looks very similar to what we obtain assuming the conservation of linear momentum. So for this to be equal to this, right, these are coming from two separate conservation law. This was obtained through the conservation of kinetic energy, and this equation here was obtained by the conservation of linear momentum. Right, so we have two separate equations, but they must satisfy both laws of conservation. So the only way to satisfy that is by getting this fellow equal to 0, right? So because these are the same, these guys are exactly the same. So for that to happen, obviously cosine of 37 cosine of theta 2 is equal to sine of 37 sine of theta 2, and the tangent, we move this one down, the tangent of theta 2 is equal to cosine of 37 divided by sine, this one goes down, yeah, of 37 degrees. And if we do the arctangent of theta 2, give us theta 2, which is equal to the arctangent of this factor here, right? And we know in the solution which we gave you, it was I think it was like 53 degrees, right? So this is the theta 2 that we asked you to calculate. Let me see if that was 53 degrees. We can calculate it right now. But it was given right here, 53 degrees. Yeah. So let's actually quickly calculate. So we have cosine of 37 divided by sine of 37 is equal to that. So inverse of the tangent of that, let me see, what is it here, of ans equal 53. Perfect. So in a kind of elastic collision, this is the kind of exercise you have to do. So now, if once you have theta 2, the rest of the problem is very easy. We can go back to the previous slides. Let me close this one. Oops. And here we go. We can essentially use this one here. Now that we know this, we substitute either V1F or V2F. We can put it down here, right? So here we have a set of two equations. These two equations, actually, we can use these two. Once we have theta 2, we can change what is V2F. Actually, V2F will be equal, right, to V1F sine of 37 divided by sine of 53, right? This will be V2F. We change V2F right here, and we get actually this one, V1F. The same thing we apply. Once we have V1F, we can use this formula that we just created to get V2F. So once we have theta 2, everything is very clear. So that's the solution to the problem, and I hope you understand things now, because there was a little bit of some maths to be done. And finally, I'm going to, because we don't have time to today, I wanted to introduce you a new instructor that we have with us, because Sir Isaac Newton is a little bit burnt out of this online teaching. So we have Albert Einstein, who wanted to explain us about the difference between elastic and inelastic collisions. He's gone to an island after the lockdown. He wanted to be alone, but he has to fish. He has to eat something, right? So he took a coconut from the palm tree, which is there, and he used what is it, elastic or inelastic collision. So obviously he is starting with an initial velocity of v1 initial, right, onto our x-axis, and the coconut here goes away with a v1 final, but has an angle of theta 1, let's say, and the shark, which was here, he was still at that time, the poor shark is moving with an angle of whatever, theta 2, v2 final, right? So let's change the color here so we can see better in this blue sea. So the fact here to understand, we're not going to go through the equations as we did before, but the fact to understand is the following. We have excited the shark, right here. The shark has been, his internal energy has changed. We have damaged him. We have this big bump here. So obviously the collision is not elastic, but inelastic, right? Anytime we start with kinetic energy and we exit with kinetic energy plus something else. In this case, the poor shark got a big bump here. So anytime this happens, anytime we excite something else in the process, these are all inelastic collisions. So this particular case is inelastic collision, and as we know, in inelastic collisions, only the sum of the momentum initial is equal to the sum of the momentum final. In inelastic collision, we cannot say in this particular case that T initial, the sum of the kinetic energy, is equal to the sum of the kinetic energy, the final, because in this particular case we don't have an elastic collision. So in elastic collision we can only use this one. This one is not allowed. Okay, this one, the T initial, was okay, but the T final we don't know, because part of the energy has been exchanged to hurt, to damage the shark, to excite the shark, or in any other process of friction, heating. Those different kind of energies will make this sign here not equal, right? Every time there's a process outside kinetic energy, there's an energy exchange which is not kinetic energy, this won't apply. Sometimes the kinetic energy plus the conservation of energy will be kinetic plus potential energy. In that case we have the total energy, but that's not what we are supposed to teach this week. Okay, with that information about how to solve that problem that was very complicated, and how to understand elastic versus inelastic collisions, we are going to end with only one another question that we all had about this particular, what they call it, perfectly inelastic collisions, right? What means in this case a perfectly inelastic collision? Basically that the coconut was kind of rotten and basically stuck in the head of the shark, and in that particular case, again, it happens the same as for any inelastic collision, but the only thing is that the final mass is the sum of the two together. So in this case we apply the sum of linear momentum, m1, the mass of the coconut, v1 initial velocity of the coconut, is plus whatever was the mass of the shark, v2 initial, now is equal, once the rotten coconut has hit the head of the poor shark, it will be equal to m1 plus m2 both together, v final, right? This is the condition for what they call it a perfectly inelastic collision. As you can see here, Albert Einstein likes very much coconuts. He doesn't like apple so much, and as you can see, everything is here in our Canva. All the videos, all the presentations will be there. And if we actually Google, with some little investigation about coconut and Albert Einstein, we see clearly that we have a winner. The whole coconut, genius. You need to drink lots of coconut if you want to be like Albert Einstein. Okay, thank you very much for this lecture, and I hope that you will have enjoyed the differences between elastic, inelastic, and be able to solve the problems, complicated problems like the one we did today. Good morning, good afternoon, good evening. Welcome to Asynchronous online teaching. Thank you very much.